Well, I want to start first with expressing my gratitude to Ukrainian Catholic University for being invited here. So it's a really great event, and I am excited to take part in this event alongside with really cool experts in fields of cosmology, mathematics, biology, and so on. And of course, to my big thanks go to my friends. One is Maxim, he's present here, and one is Andrew, who's not. And I want to thank them for their contribution into these two lectures. This contribution is really indispensable. And of course, I'm very happy to be once again able to deliver a lecture for living audience instead of speaking into some inanimated computer screen that that makes me feel like talking to the wall. So talking to living people is much better, believe me. Okay, so let's get started. So I want to tell you today about the topological data analysis and its use in natural sciences. I will be mostly focusing on the mathematical apparatus that stands behind all these things, but since we are scarce on time, I thought that I would have 1.5 hours per lecture. It seems like I have only 50 minutes, so I was misinformed. Well, not so much as to search water in Casablanca, but I was still misinformed. Okay, so I'll be skipping some large parts, and let the mathematicians forgive me. I'll be very sloppy on my definitions and statements, well, as much as I can. Yep. Okay, thank you. Okay, so so let's get to the gist. First of all, topological data analysis is some sort of umbrella term. So there are different methods that are called this way, and they do quite different things. So what I want you to tell about today is we will have 2 lectures. So first lecture, I will tell you about so-called manifold learning methods. So that's a subfamily of methods that allows you to reduce the number of dimensions. So these lectures will be about basically about the dimensionality reduction with the help of topology and appropriate methods. And the second lecture will be based on my and Maxim's recent work in cosmology. We were using some interesting mathematical apparatus that is called well, homologies, different homologies, and persistent homologies, and I'll try to show you how to use that and what to do with that. Okay, I'll skip this part. Maybe we'll return to that a bit later. I wanted to present you everything more rigorously, but there's no time, so let me explain in plain words. So topological and data analysis. So what is data analysis? You are basically analyzing some data set. What is a data set? That's a collection of some data points. You can think about a data point as some point, no pun intended, in a higher dimensional space. And each coordinate that this point has is basically some feature that you have. So you want to work with some collection of features, and they give you a data point. So they live in some higher dimensional space. Of course, we can do much with separate points with the topology. We need something more. So what we are basically supposing that we have some sort of a manifold on which these points lie. So probably if you don't know what is a manifold, and I'll try to skip all the rigorous explanations, so let's do it some hand-wavingly. So suppose I'm now in some ambient space, so 3-dimensional. Oh, seems I broke my manifold. Okay, here are my data points. So they now live in a 3-dimensional space. So I can basically prescribe to each of these points 3 numbers that signify 3 dimensions of the space. But you can see that these points are basically placed on some surface. It may be curved somehow. It may look quite differently from a plane, but what is the defining property that if you take any point of this surface and you look around in a really small neighborhood, it looks like a plane. And what we'll be doing with all these topological methods, we'll be playing around with that manifolds, and we will try to do something with them. So basically on this lecture, we'll be trying to squeeze these manifolds into a lower number of dimensions. So for example, if I have some coordinates, it can be something very complicated. But I will show you methods that will try to put all these points into a plane without losing some patterns that exist within these points. So they have some relative positions, and in their relative positions there may be encoded some information that you want to know, and you want this information to be kept. What can be that information? So for example, for a physicist, suppose I have some massless rod and I have a mass attached to it. So a simple pendulum, nothing more, nothing less. Suppose this pendulum swings somehow. And I'm getting my data set by exploring where is this mass. So what would I get as my data set? A number of points in 2D, so two numbers that are associated with this pendulum. But if I consider it a little bit deeper, I will understand that all these points, they can lie on a circle only. So they all are restricted to the circle. So basically this is one-dimensional system, so all points live on a manifold. This manifold is this circle. It has lower dimensions than 2, so I can basically reduce the number of dimensions to 2, from 2 to 1, and I will still keep information about my pendulum. So physicists know that when we are going from two-dimensional coordinates to describing this pendulum in terms of angle theta, for example, or something like that. So that's what we will be trying to do. And why do we want to do that? There are basically many reasons. So first of all, you can understand your system better. So that's example number one. Number two, that helps you eliminating noise. So if I have some noisy data, so I can't measure the position of this mass precisely. It can be a little bit noisy. But if I take all these points and I will forcefully put them on that circle, I will basically eliminate some noise, basing on the properties of the system. One more example, you may want to draw your system, so you want some visualization. Of course, you can't visualize data that has, I don't know, 100 dimensions. So you need to draw some picture. In picture, you can show 2 dimensions, maybe 3, but no more. So you may want to squeeze all your space into 2 or 3 dimensions, but you don't want to do just some cuts or something that's simple. You want to get something more. You want to somehow preserve some properties that your data points have in their relative positions. So you do something more, let's say, smart. And you probably know at least one method of dimensionality reduction that is called PCA, so Principal Component Analysis. I will briefly show you how it works because its work is quite similar to the manifold learning methods, except the fact that it performs only, let's say, affine transformation, while manifold learning methods will allow me to do something more sophisticated, some nonlinear transformation of my manifold. But let's check out as the simplest example, PCA. So here is my data set. Coordinates x and y, obviously these are 2 features. So whatever they signify, so some features. And here is my coordinate system. As you see, if I take projection of these points on axis x and axis y, I will see that they look, well, they somehow look, so nothing interesting. But what happens if I'll try to transform this coordinate system? I'll try to move it around. More interestingly, what if I try to rotate this coordinate system? It can happen that I rotate it so nicely that I have almost no deviation from 0 along one coordinate, so that's y, oh, that's x coordinate, so almost nothing changes. They all sit near 0, and I have all the variation along the other coordinate. And we say that since this variation most probably carries some interesting information about our data set, it's really what we want. So I can eliminate one feature after this transformation, and I will retain the other feature that basically contains almost all information I need. Okay, so what about manifold learning? We will be basically doing the same thing, but we'll be trying to work with some more and more sophisticated functions when trying to squeeze all that points into some lower dimensional space. So they can be highly nonlinear. It can be something really sophisticated. And I'll show a few methods that we'll be dealing with. But first of all, small TDDs of so-called test-driven development. So before we start developing our methods or basically learning them, I'll show you some examples on which we can test our methods. So the first and the simplest test is testing on a plane. So we have a plane in 3-dimensional space, and I would like to settle this plane somehow into 2 coordinates. So just leave x and y and nothing more. So of course, you can do that with PCA because it's just a affine transformation, but our methods of manifold learning should work at that. Why not? 2 more examples of manifolds. So hopefully you get the overall intuition, how do they look like and what are we trying to do. So one manifold is S-shaped, so you have some sort of letter S. You can think about a piece of paper that is formed in letter S, and the other one is so-called Swiss roll. And you have points on these manifolds, and of course you are trying, in case of roll, for example, unroll it, so or in case of S, to stretch it somehow out, put it into the plane, and thus eliminate at least one of the features. Here's an aside how Swiss roll really looks like. And moreover, we'll be seeing many pictures. I'll draw, for example, and they all look like some sort of art. So maybe you can even recognize what kind of art it is. So if nobody knows, that's pointillism. Yeah, I'm not sure I'm pronouncing that correctly, but it's a drawing with some sort of dots. Pointillism. Oh, thank you, David.
Machine learning to create that image, yes? Understandable, this is machine learning to create the image, not?
No, it's just to show that we will be seeing some images in these presentations that look like that image. That was created by a human. So, yeah. That's Paul Sagnac. Yeah. So, and here we start going with our data sets. Well, basically, these examples were part of my course at Kyiv Academic University, so you don't, so it's okay to have such sort of data sets in here, or you can think it's a product placement. Okay, so what do we want? So here is some collection of points. I have assigned colors to these points, so you can see their relative positions to each other. So they are somehow positioned in relation to each other. And what I'll now do, I will take these points, I will place them on some manifolds, and I'll try, of course, to keep the relative positions of these points. You'll see that. And then I will employ all the methods I know on that data sets, and I will expect that they return me, well, something like this. So let's give it a try. Here is a sort of example I want to show you before we will dive into all that mathematical details. So here are the methods that you have in sklearn. So library sklearn basically provides you a number of functions that you can use, and of course it provides you a number of functions that basically do manifold learning. So here is my example. So you can see now the manifold I'm using. It's S-shaped manifold. If I move it around, you probably can see the letters I have put on that manifold. And And what we want from our methods to unwrap it into two-dimensional space in such a way that it somehow retains the relative positions of the points. And now you can see, for example, some modifications of LLE methods. LLE method. We will talk about it a bit later. So as you see, some modifications are doing pretty well. So pretty well, they almost reconstructed whatever I had initially. Of course, I can't expect the perfect reconstruction because these methods cannot read, they don't understand that there are some letters or something like that. But relative positions of the point, are really good. And here you see a few methods that weren't able to do so well, so MDS couldn't handle that. But still, if you see colors, you can see that some information at least was retained. So it didn't fail miserably, it just failed. So isomap did, well, not so bad actually. So we have a number of methods that are capable to do that. And probably we can use them on some higher dimensional data if we need. One interesting thing to notice that I probably forgot to say is the fact that when we are using these methods and we are decreasing the number of dimensions, that's really good for any subsequent machine learning methods we will employ after this dimensionality reduction. Why? Because we have so-called curse of dimensionality. The more dimensions we have, the worse our machine learning methods tend to work. So if you have all this machinery that helps you to eliminate some redundant features or to make somehow smaller number of features, that would be really great because you can make your subsequent methods to work better. So these are even used to inject information into neural networks. So probably it should be useful if people write articles about it. Okay, so the first method, MDS. So multi-dimensional scaling. There are few modifications of MDS. I will show you a so-called metric MDS. Of course, we can't go through all of them. It's too much information. It's a very simple method. But what I want to show you is that it's almost intuitive. It's almost intuitive. Consider once again. Consider my manifold and points on this manifold. Now I'm telling you that I have a problem of putting this manifold into 2D. So I want these points to live on a plane. How do I do that? I want somehow to retain the relative positions of these points. So the first idea that may come to your mind, why don't I just measure distance between these points, and why don't I just require that I need to have some function that puts all these points into the plane, but retains distance between them? Of course, I can't expect this distance to be retained perfectly, but why don't I minimize with respect to an error that I get? So that's quite a simple idea. Why not? So I measured some distances, and now I want something like that in the plane, but I want all the distances to be conserved. Great. How do I do that? Quite simple. I can calculate the matrix of distances. You can see matrix D right here. So I'm just taking all the possible pairs of points I have, and I am calculating distances between them. So that's simple. Then I do some function, I do some transformation, I put them into the plane. That may be quite simple as well, because we care about only how these functions carries our points of interest, our data set. So you can basically build some sort of table when you tell I assign this point to that point on a plane, and so on. And you can calculate matrix of distances in the plane. Still simple. We had distances there, we have distances here. How do we calculate an error? The same thing. So you can find distance between these matrices, and you do maybe the simplest distance possible, so-called Frobenius distance. You just find differences between corresponding elements of the matrices, you square it, and you add everything up. It looks the same way as if you worked with, I don't know, if you stretch this matrix into a vector and you do, I don't know, difference between that vectors and square it. So not much difference. And you can now perform a minimization of this problem. And that's really good. Why? Because machine learning is always about we are minimizing or maximizing something. So at the moment that we arrive to the problems that is basically minimization or maximization of something, it means that, yay, we can do that. Because we have a number of methods that can solve this kind of problem. Okay, now let's check out how it performs. Here is my first test from the TDD. So there's a plane in 3D, and I want my MDS method to somehow reduce the number of dimensions from 3 to 2. Here's the code in Python. I won't get into it. We don't have time, unfortunately. But I want you to see the results. So you see that all these points were perfectly placed into the plane. So basically that's the result you could expect from PCA, for example. And you see that MDS does perfectly this job. But still, why do we have so many methods of manifold learning? They don't always work correctly, so sometimes we have some problems. And MDS fails if we tend to work with some highly nonlinear manifolds. So here is an example of such a nonlinear manifold. You probably saw that already. So that's the letter S. I'm trying to rotate that to show you the structure of the manifold. So how did I paint all the points? So you can see their relative positions. Basically, I should remind you that all these algorithms, they don't see any color. They don't know how did I color the points. They only know their positions. So they are working with their positions only. And whatever I get from that, I am just recoloring in the same order I have colored the original manifold. So that's the crucial point. We can see with the help of that coloring what was broken and what played out well. But so the algorithm cannot, he doesn't know that. And here is how MDS works on the S ladder. So we see that it fails somehow. As I told you, it didn't fail miserably. So points are not some scattered around in some random pattern. No, there is some pattern to that, but it's just not what we expected from it to have. So we have this form of ladder S. Okay, so what should we do? Our method failed, but we want something more. And it just happened. It's quite an interesting story. Here is the number of journal Science for year 2000. And in the same number of this journal, 2 articles were published. Each of these articles solved the problem of bad working MDS in its own way. That's really an interesting fact. By the way, do you know what is this cover page about, this title front page of the journal? Nope. That was, yeah. No, this front page is about Human Genome Project. It was completed somewhere around 2000, and I remember very well it was a very big event, and even TV did the announcement that we completed the Human Genome Project.
Problems of
So, okay, and in this journal we had 2 methods that I will cover now. The first one is locally linear embedding, or so-called LLE. And here is the nice picture. What does this method make? Well, basically we make use of the definition of the manifold. I told you that manifold locally always looks like some sort of lower dimensional space. In this case, we are living in 3 dimensions, and manifold is 2-dimensional. And we are trying to make use of that. So when I take any point from the data set and I look around in a small neighborhood, it looks for me as a plane. So I can think about such an interesting idea. if I have a nice function that can take all these points and place them somewhere into the plane, locally, this function should look like a transformation of a small cut of the plane. So locally, it looks like a affine function. So just like translation, rotation, something like that. So it's really locally, it looks like a affine function. Okay, now we know that affine functions, if we calculate an affine combination, it will be conserved. So affine functions do not change affine combinations. If you don't know what is affine combination, I will remind you that I can take some elements of the space, I can add them together, like you add, for example, some vectors, with some quotients. So it would be just a linear combination, yeah? But if I say that I want these quotients to add up to 1, that would be a affine combination. So it's good because affine combinations, they are not changed under the affine transformation. And what of that, would you ask me? We can build an algorithm based on that. Here you see small patches. We find around each point of the data set its closest k nearest neighbors. We just find them. We solve for a so-called reconstruction of weights. So we say that this point that we are interested in, we want to express it as a affine combination of the points that are sitting around. So I'm writing it like some sort of sum with some quotients wij, and I say that they should be equal. Then I tell you that if I have a right function to transform all this manifold into the plane, these things should be conserved. So the new coordinates of my target point and the points that were around should change in such a way that if I calculate once again all that weights, they should coincide. So that's what I want. And here is the algorithm that was proposed. So we find k nearest neighbors, we solve reconstruction for weights, and we then minimize the embedding. We search for the function that tries to conserve these weights. And then we reiterate until we get some sort of convergence. Here are the exact formulas, but I know that it may be too hard to see all that just in one slide. So what I want you to carry out from this slide is the statements that LLE, so locally linear embedding, is some sort of sum of local MDSs. So instead of doing the multidimensional scaling of the whole manifold, I'm working with small patches. And that work with small patches, it basically can be formalized in some way, and you get LLE. Okay, I feel that you that you are tired, but let me show you some nice pictures that will explain to you what's really happened right now. Here you see my data set. So 2 letters S. Of course, you might think, what are these strange black things? As I told you, MDS takes into account all the distances between the points that we have in our data set. So I have drawn some of these distances. And you can see on the right panel which distances MDS used. And you might see that where the problem lies. So if I have manifold that looks like something like this, and if I'm trying to take into account this distance, it's very bad when I will try to stretch this manifold. So you see the problem. You may see that we have a lot of distances, so-called parasitic distances, that tend to go from the upper left corner to the lower right, and they don't give me to stretch that manifold as I want. But what does LLE? Look at the left panel. Here is some of the distances that LLE uses. And you see that with the help of considering of that local patches, I'm not having that parasitic distances. So now nothing prevents me from stretching that letter S and putting it into the plane. So the main idea I have in this way, I have removed some of the distances that were basically parasitic and that didn't allow me to perform my minimization and put everything into the plane. So this is the main point I want to show you. Of course, there is some math behind it I showed you before, but okay, let's leave it as it is. And time for testing. Here is the result of LLE that I have run on that S-shaped dataset. And you might see that it has unwrapped it successfully. So at least this method on this kind of manifold worked quite well. So all the relative positions of the points were retained. If you flip it bottom to top, you can see almost the original image. Okay, the second method that was published in the same number of the journal is called ISOMAP. And it solves the problem of MDS quite differently. It's very sort of interesting. So two like engineering approaches to the same problem. So we have MDS. We have problem of that parasitic distances that prevent me from unwrapping my manifold. So that brings me some problems. So how do I solve that? LLE tells me, throw away. Throw them away, everything will be great. Good. The other way is ISOMAP. It tells me, don't throw it away, fix it. So make that distances more or less reliable. So what do I actually want? When I calculated distances in the MDS, I was using the metric of the ambient space. So basically, I was calculating distances in Euclidean space. But when I have the manifold, it seems to be much more correct to calculate the distance along the manifold. So I should calculate some sort of geodesic distance. And that would be the correct distance. Why? You can see these two points on the image A. So they are close to each other. If I calculate the distance in the ambient space, I get some sort of small distance between them. That's a parasitic distance, and that would prevent me from unrolling that Swiss roll into the plane. That's bad. But what if I calculate some better distance, so distance on the manifold? I will get a long distance between them, and that would be great, because when I'll be unrolling that manifold, I can fit it into the plane. Of course, there is a question, how do I calculate that distance between the points, especially if you noticed I don't have the manifold itself. I have just a data set with data points. And here comes another assumption. If we have enough points to cover all these manifolds, so we have many manifolds points and they are densely set on the manifold, I can try to find distance by moving from one point on the manifold to other point. So what we are doing, we are transforming them into a graph. When we are connecting each point to some number of its nearest neighbors, this graph will have edges that basically have some length. And I can move along these edges and find the shortest path that I can between points A and B. So here is the image C, shows you how it looks like if it's unwrapped. And you see the actual geodesic distance that we should have between points A and B. And we see some approximations that we can get with our graph shown in red. So probably, yes, it will somehow differ from the real distance, but it's much better than calculating the distance in the ambient space. How do you find that closest distance? Well, basically, computer scientists know at least a few methods to do that. For example, you can calculate shortest path with Dijkstra or Floyd-Warshall algorithms, so you probably know something of that. I don't know, I shouldn't maybe get into details of those algorithms, but they are quite simple, believe me, so we can do that. And when we are reconstructing all that graphs, we are calculating distances, we are basically fixing the broken distances that we had in MDS. So parasitic distances become more correct. So what I want you to take away from all these slides is that isomap is MDS but with geodesic distances. So once again, everything is based on quite a simple idea that we have in the beginning. So we had a manifold, we had some points, and we want to squish that manifold into some lower dimensional space, retaining the relative position of the points. To retain that position, we had the idea, why don't we just measure distances between these points, and then we just say, I want such a function that puts them into a lower dimensional space and retains all that distances. It turns out to be not very well in some cases, but when we fixed it here and there, for example, with isomap, we said, okay, I need a distance, but not just distance in an ambient space. I need some geodesic distance along the manifold, and I know approximately how to calculate it. We get isomap, and isomap, once again, works quite well on the data sets I have. That should be XS, then it's S-shaped manifold. Okay. Here's one more example for you. I'll try to run everything. Yeah, we still have some time. It's really good. So I'll be able to show you some more examples of unwrapping. And I really encourage you after the lectures, if you want to find all these things, they are all freely available. They all start in Google Colab, so you can just play around with all these things and look at them more carefully. So this demo shows you basically what happens when you employ some methods of the sklearn to different manifolds. So here you choose the manifold, so I chose for simplicity just plain 3D. You choose a method, for example, locally linear embedding, and you choose the number of neighbors, because LLE and isomap, they actually need these parameters parameter to work. And here you see my data set, and on the right panel you see what happened after I put it through that method. Okay, now let's do something more sophisticated. So you can take, for example, some mobile strip and try to do something with that. And with this example, you can basically experiment and look what happens when you take more neighbors, less neighbors, some more complicated manifolds. They are basically predefined by me, but probably you can understand the code and add something more. So here is the mobile strip. Let's check something even more sophisticated. I guess helicoid. This should be the case when LLE fails, but isomap still should work, as I guess. So let's check it out. Yeah, so you see the helicoid, and well, you probably need some imagination to recover that letters I had in my initial manifold, but probably letter K is in here. But you see that LLE was not able to do something with that, so it failed. But if I take, for example, isomap and I try to unfold it, I guess it should work. And you should maybe think for a while why. I won't give you an answer, so that's a question for future. Okay, it's few more examples just, and we'll be done. Okay, so it processes. Good. Okay, well, it processes. So let me. It completed. Great. So now you see that isomap was able to unwrap the helicoid and put it into the plane. So yeah, it's distorted somehow, but if you look carefully and you think in terms of like flipping top to bottom, you can see once again the ladders I have put in my initial data set. So it's basically did its job. Now about some, yes, please.
Isn't that non-efficient?
Yes, you're right. These methods take quite a long time to run. So you probably, if you have a large number of features or a large data set, you may have troubles with that. That's pretty true. But there are cases when you want to involve these methods. So it's not so catastrophic, so you can use them in many cases, basically. And right now, I'll show you the case, for example, of images. So let's look at these images. Each of these image contains approximately something like 1,000 pixels. So if you think about each pixel, its brightness is a feature. So it's basically a brightness of light at some point of the photo matrix. You have a 1,000-dimensional space. And I will take all these photos and put them into our manifold learning methods. So I'll just take this 1,000-dimensional space and I put it there. And what I want it to do is to squish it into 2 dimensions. And here you can see the result. It may look first strange for you, but if you ponder on it for a little while, you will see that coordinates that our methods retained are meaningful. For example, the overall brightness of photo is changing from the left to the right. So you see that the brightness of the photo, the overall brightness, is changing. So it would be more probable to see, for example, Barack Obama on the right and Donald Trump on the left. If you look at the direction that the face is looking, you see that if the face is on the top, it's more probable that the head is turned to the left. So it's looking to the left. If it's on the bottom, it's more probable it looks to the right. And here is the interesting thing. I want you to think about it. So we had a method that just works with a data set. It has no information on what is a picture. It has no information of what is a face. It has nothing. It has just a bunch of numbers that can represent a point in space that can be basically anything. It can be something generated. It can be state of the physical system. It can be position of the halo in cosmology. It can be anything, basically. And it did some analysis. It turned 1,000 coordinates into 2. It's almost like nothing. You can do that with PCA. If you try to do PCA and you want to retain, for example, 90% of your variation, so you want to retain some information in that, you will need something approximately 100 components. Compare 2 components and 100 components to retain some sort of information with PCA, and what you get is still meaningful. It really looks cool. One more example for you, visualizing structure in handwritten digits. So we have a MIST data set. Very simple, very small, but each picture is 28 by 28. So you do the math, how many coordinates that is. So it's something around 900, yeah? So once again, we have a very highly dimensional space. And I tell to my methods, okay, let's take all of that and squish it into, let's say, 3 dimensions. And here is the result. Different colors signify different digits. So I didn't do the legends, so I don't actually know which one is which. But it doesn't really matter. What I want you to appreciate is the fact that they are clustering somehow. So you can look at them and you can see that there is some clustering. Remember, I'm squeezing 900 coordinates into only 3. It sounds like nothing. All information should be lost, but it's not. And when we see these clusters, we can appreciate the fact that if I have some machine learning method that will, for example, will somehow distinguish between these numbers, so I want it to distinguish somehow. And if I put into it not the raw picture that having all of that, but what comes out from my manifold learning method, it should be quite easy to separate all that digits one from another because they are clustering. And the last example for today is the number 1 from the same NIST data set. And once again, we put all that dimensions into only 2, like we did with faces. And you can look at that numbers 1, and once again, you can search for some patterns in here. So what do we have? And if you look carefully, you will see that on the left, we tend to see ones that are written from the top right corner to the bottom left corner. When on the right, we tend to see ones that are written from the top left corner to the bottom right corner. And in here, we see some ones that have this small bar at the bottom. So once again, our method found some structure in our data set without even knowing what we are working with. It doesn't know that it's image. When you put it into neural network, it knows that it's image. It performs some sort of convolution and so on. So you have some geometric relation between your pixels. So it knows that these pixels are closer to each other than that one. For this method, it's just a bunch of numbers. It's some coordinates, no matter which one is which. And it still helps you to find some pattern. In conclusion, so what I want you to say, these methods are basically quite powerful, as I think. They may help you to visualize your data to get nice picture. They may help you to get some insights into your data. So maybe you will see in that picture something, some patterns that you cannot see in your data set. If you have a 1,000-dimensional data set, what can you see there? How do you draw that? With this method, you can do that and at least try to search something. They can help you with feature engineering and extraction. And of course, with noise filtering. So once again, the example of the pendulum. So if I know that all my points should be situated on that exact circle, I can use this fact to make my data better to remove some noise. Of course, there are a number of problems. So I should say about them, because no method is perfect. So we all know that. So first of all, in manifold learning, we have no good framework for handling missing data. So if some data is missing, some features are missing, we are in trouble. So we should solve that somehow. In manifold learning, well, presence of noise in sometimes can short circuit your manifold. So if I have too much noise, these methods cannot, maybe not able to see through the underlying manifold. That may be a problem. You have no, let's say it, inverse transformation as PCA does. Because we are basically concerned on where do our points of the data set go. But with PCA, we have the overall transformation of the whole space, so we can transform to one side or another as we want. So here we have such a problem. Yes, they are expensive to calculate. That really was a right question, because these methods, they scale as n squared, or sometimes even as n cubed. So that's a really bad. While for the PCA, there exist some randomized approaches that tend to be much faster. But probably with some time, maybe some one of you will find some methods that allows us to make that quicker, maybe some randomized method or something like that. Well, with that being said, I think I use up all my time. So thank you for your attention, and I'm ready for questions.
Thank you. My main question is about distance. That's a painful question in all of this stuff. And how we could account the anisotropy? Because everything you have done so far, that's pretty isotropic, and those data points are scattered evenly. So how we could include the more complicated structure over the manifold, and how we could escape isotropy assumption.
Okay, thank you. So yes, first of all, I have treated all the features equally. That's maybe not the case. So yeah, that happens. In most cases, we will try to do some sort of normalization of features. So we'll try to make them look more or less uniformly for us. So that's the way we do. Well, in other cases, that may basically just don't work. This method may sometimes they may play out well, sometimes they may not. So in any case, what we do, we are doing this method and we are trying somehow to test is it good or is it not, as we do with any engineering method. And the way of testing this, for example, that I can propose is most cases you do this method, you put the results into some subsequent machine learning model, and you look if it performs better or worse. Because we have method to test that. So we know how to do if we have classification problem or whatever. We can draw all that confusion matrices, so on. And we see that here we have nice confusion matrix, here something went wrong. So here we have nice F1 parameters, here we have something not so good. And we can assess in such a indirect way how good is our manifold learning method. So is it revealing some underlying structure of our space, of our data, or is it hiding from us? It can be both ways, because no method is perfect. But of course we expect that in many cases it will play well.
Let's say my question is more, if we try to do the same things, but including anisotropy, we will be the pioneering, or what is the state of art of these methods?
I guess trying to include isotropy maybe something pioneering in this way. Yeah, because these methods they are used now, but most people are now turning their faces to neural networks. So we all know that. Right now, some people try to use it with neural networks. So here is some sort of examples I tried to show you. Well, I was, I guess, too lazy to put citation on it, but that's from one of the articles. And as you see now, people are trying to somehow to marry these methods with neural networks. So we are injecting, except the initial information into the neural network, we are trying to inject some topological information. And that may be result of, for example, these manifold learning methods or some different methods that extract you topological features.
Visualization complex neural network. That's the possible application.
Maybe yes. I can't answer that from top of my head. Yeah. Yes, please.
Oh, I have a microphone. So I think I might be wrong, but I think there is one particular method your research is lacking, and it's usually very underestimated across experts overall. It's hierarchical clustering, mainly dbScan. And I see you've used TSNE, LLE, and many other methods, and problem with them is they are either difficult to maintain to configure or long time to train, especially for TSNE. And the benefits of dbScan, for example, it's you configure just 2 parameters and they're really easy to maintain if needed to retrain. And I think I haven't seen any of hierarchical methods, but have you looked into that direction?
Well, as far as I know, dbScan is the method for clustering.
That's not hierarchical.
Anyway, dbScan, hierarchical methods. So because I faced similar problem, and I was advised to try to look into that direction.
Since 1970s, dbScan was called top hat or Mexican hat and widely used in cosmology for clustering. So the same names are going, and most of these tasks, and exactly we're involved right now in collaboration. We use the dbScan, but that will get different names.
Yeah, thank you. I want to point out that there is a bit discrepancy in the problems that these methods solve, because when you do a clusterization, that's one problem. The other problem is the reduction of dimensions. So you don't, yes, of course, I showed you some clusters, but it's just to show you that some structure in data is retained. It didn't perform any clusterization. It performed reduction of dimensions. So you put in there some, I don't know, 3 numbers, and you get 2 numbers from that. It's everything it does. So it's a machine that performs you that reduction of dimension. whatever you do with that result, it can be basically some clusterization. So probably these clusters will be better seen. So what I showed you with MNIST is that the clusters can be better seen. So you can employ some algorithm on top of that. So be it dbScan or I don't know, whatever you use, it will find you that clusters more easily, because it will have to deal with 3-dimensional space only, not 1000-dimensional. So that is the case. So it's a little bit different cases. So you can use in conjoin these two methods. So you can use reduction of dimension, then some clusterization. But these methods, they do not clusterize anything. And that's why I always pointed you out that it's really a miracle that the structure in data is preserved. This method that does not know anything about any clusters, any nature of the data, nothing. And it's still, when it works, it preserves some structure in it. It still retains some information. That looks for me really miraculously. Yeah.
Thank you for the very nice story. For better understanding, these distances you were using, they are distances in a proper sense. So you have the triangle inequality, for example, which holds always, right? Thank you.
For the MDS method, so I was using the ambient, the distance in the ambient Euclidean space. So very simple. Of course, it's distance in all the respects. And when we are going to the isomap and we are changing, we once again, we get some approximation of the distance. Because what we want is that geodesic distance, that is, of course, a proper distance. But we get some approximation because we don't have the manifold, we just move from point to point. So it's almost that simple, yeah. Yes.
Okay, so my question is which domains this method is most using, because in the examples and from what I found, I've seen mostly image processing, so would it make sense to use it as an example on something like, let's say, a generic Kaggle tabular data set, like housing pricing, where you have some categorical variables and some continuous and so on.
Okay, thank you. So I guess it's most useful when you have some sort of continuous variables, because what you want at the end of the day, you want your points to lie on some manifold. And if you have some sort of discrete data, it's hard for me to imagine how would they cover the manifold. So it's really good if your data points can cover that manifold, and that's why they should be some sort of real numbers. And of course, it would be really nice if you normalize them and perform all that stuff, because we don't want our manifold to be too strange, let's say. So that's the best, I guess, data that it can work on.